Now let's understand the concept of inductance. We have used electromagnetic induction. So from induction comes inductance. What is inductance? Let's see. You know, inductance. What we have seen that the flux is proportional to I. We have seen this. We have seen d phi b by dt. It is proportional to electromotive force, which is proportional to I. So we can say this is the case. Okay. So from here we get phi flux is proportional to I. Here comes another term which is called flux linkage. What is flux linkage? Let's say phi b is due to one loop. If we have n number of loops, then n phi b, this will be the flux, because of every turn you have phi b. So if there are n number of turns, n phi b is, this is called flux linkage. Okay. So obviously n phi b is equal to I. Now to eliminate this proportionality constant with equal to sign, we need a constant. So this is actually n phi b is equal to, let that constant be k, ki. This proportionality constant is called inductance. Okay. And there are two types of inductances. First is called mutual inductance. That is, if you have two coils, first coil and second coil, if there is a current, okay, because of this is n phi b, and because of this you have current I induced here, then this proportionality constant is mutual inductance. That is because of this, mutual. And another is self, that is called self-inductance. This is, we use the alphabet M for this and we use L for this. This is how, this is when you create a current in a coil. Let it be bigger. If this is a coil, okay, and this you have di by dt, the current is changing, this will set up a flux linkage that will be equal to L into I. So this is because of the own coil. The current is varying, the flux will vary, and that changing flux will create current, another current which will oppose the original current. That is called self-inductance. And this is mutual inductance because of another. Okay, so let's see one by one. First of all, we'll see mutual inductance. So first of all, see mutual inductance. Let's say we have a coil here. Okay, let this coil be number 1, and we have R1, associate the radius of this coil. Let's say the current is I1, phi 1, everything for this first coil. Now let this coil be inside another coil. This is the second coil, inside which you have this coil, and the center line is common, it is coinciding. Okay, so let this be 2, coil number 2, the smaller one, and this be coil number 1. Okay, this is 2. Let the variables be R2, N2, flux due to this be phi 2, I2, everything with subscript 2 for this and subscript 1 for this. Now if we connect this coil to a voltage source, a current will be set up, this current I2. So let this current be I2, and because of this you will have a flux linkage in the coil number 1, the outer coil, which will be given as N1 into phi 1. You know, this is flux linkage. This will be equal to M in 1 due to 2. We write mutual inductance like this. That is mutual inductance in coil 1 due to coil 2. We have current in coil 2, which is I2. This will create flux linkage in the first coil. Okay. Now we can find what is this M12. How we can find? See, we can find M12 from here only. See, M12 into I2, this is N1 phi 1. Now let the number of turns be this. We have to first of all find what is this N1, this capital, that is the total number of turns. If the number of turns per unit length is this one, small n1, and the length is, let's say this length is L1, okay, and this length is L2 from here to here. So this will be N1 into L1. This is this thing. Phi is what? B into A. Phi is BA. This you know. Okay. What is V? V is, we have found for a solenoid, it is mu Ni. This is B, not N, not capital N, N per unit length. This is, so we'll write B, this magnetic field, this will be mu 0. This is magnetic field is due to coil 2, so this will be N2 mu N2 I2. It is I2. The current is I2 into area. What is the area here? If the radius is R2, the area is pi R2 square. Clear? So M1 2 I2. So I2 cancel from here. What do you get? You get, see, mu 0 and pi I am taking out. So what you get? N1 N2 L1. Okay. So this will be mu 0 pi N1 N2. Okay, mu 0, this is mu 0, this is pi N1 N2 L1 into R2, not R2 square. See, this is phi 1, so area will be R1 square. See, phi 1 is B into A, so this will be B into area is pi R1 square. So this will be R1 square. Okay. Now let's say the two lengths are equal. That is, this solenoid and the solenoid above it, they have equal lengths. Then we can say L1, L2 as L. So let's drop the subscript. So from here, you know, it is M12 as this. What about M21, that is mutual inductance in 2 due to 1, if we want to find that? So let me rub this. If we talk of M21, obviously this will be due to 1 I1. That is M21 into I1 will be, flux linkage will be in this, that is N2 phi 2. So what is this? It will be, N2 will be, this is per unit length into the length L. We have taken length L1, L2 equal to L. So this is this. Then phi is B into A. What is B? B is mu 0. Then what is magnetic field? Magnetic field is mu 0 N1 into I1. Okay. This is the magnetic field, and area is pi R1 square. Sorry, pi R2 square, phi 2. So this is this. Clear? Current is now in the first coil. So magnetic field is this. This is, okay. So this is B. What area? This is, flux is in this area only. This area only. So that will be pi R2 square. So what you get is mu 0 pi N1 N2 L. Then you have R2 square. Okay. So what you get? You get M21. This I1 gets cancelled. This. So M21 is simply this thing. Just to rub it. Now, if you see, this is equal to M12. That is, mutual inductance of solenoid 1 due to 2. This one is equal to mutual inductance of solenoid 2 due to 1. So we simply denote it by M. Okay. So this is mutual inductance. And you know, this is for vacuum, it is of free space. So if you have certain material inside it which has permeability of this, then you can write mu r mu 0. So this is clear. Now you know N2 into phi 2, this is equal to mutual inductance M into, it will be for 1, so let's say for N1 phi 1. For N1 phi 1, this will be M I2. This we have just seen. What if we take this? Sorry, this d by dt. So it will be M di2 by dt. So we say electromotive force is minus d, this thing, N1 phi 1 by dt. This will be the electromotive force induced in coil 1, which is d phi 1 by dt. So in place of this, you can write minus M di2 by dt. So if you know the mutual inductance between the two coils, the value of this mutual inductance, so electromotive force in one will be minus M di2 by dt. That is, if you know what is the rate of change of current in the second coil, you can find the electromotive force in the first coil. Okay. So we have seen mutual inductance, we have seen the electromotive force due to mutual inductance. Now let's see self-inductance. I told you, if we have a coil and the current is changing with respect to time. Let's say this is our coil. Okay, the number of turns is n. The current is actually changing with respect to time. Then the flux linkage, if this is n phi b, this will also change. Now, because of this change, a current will be induced in this, which will oppose this. That is, if the original current is I, then because of this current, we have a flux of this in this core. Now, because of this, you'll have another current which will be actually opposing this. This is due to self-inductance. That is, now let's come to expression. We have n phi b proportional to I. Okay. So from here we have a constant, that is n phi b is a constant into I, which is given as L. This is self-inductance. Okay. So you have electromotive force as this. So you can write it like this also, minus L di by dt. Okay. Now let's calculate what is L. How we can calculate? We can calculate using this expression only. So L into I is n into phi. N is what? If the number of turns per unit length is n, if the length is L, so this is n. Phi is B. B is what? Mu 0 n into I, and area. Area is what? It is pi into, let the radius be r square. So this is your area. I gets cancelled. So L is n square. N square. Then you have, see, n square. Then you have L r square mu 0 pi. This is self-inductance. Or if you write this as A, you can write it as mu 0. I'm taking it out. So this is n square L r is not r square A. Okay. So this is also an expression for this. So this is self-inductance. I think this is clear to you. So now when you know this, let's calculate what is the energy required to induce current I in a coil, which is actually stored in the coil. See, power is dW by dt. This you know. If the work done in producing the current I is W, then dW by dt is power, and power is voltage into current. This you know. So it will be mod of this into I. And what is this? This is, you have seen, L di by dt into I. So you can put it like this: L I di by dt. This is dW by dt. So dt cancel. Now if you want to know what is work done, let's say it is done in from I di. So from 0 to current I di. This is L. So what you will get? I square by 2. So this is half L I square. So this is the work done in setting up current I in the coil. This is actually stored in the coil. Later on you will understand that this is the energy that is stored in a coil which has self-inductance of L, and a current I had been set up in that inductance in that coil. Then the energy stored is half L I square. Now finally, let's see one more expression. If we have two coils, this is first coil and this is second coil. Let's talk of coil number 1. This is coil number 2. Then electromotive force set up in the first coil will be equal to, or first of all, let's see the linkage. N1 into phi 1. This will be equal to, first of all, because of its own self-inductance, that is L into I1. And second, mutual inductance into I2. Okay. Secondly, if you talk of electromotive force, this is equal to, this will be equal to what it is? It is L di by dt. So it will be minus L di1 by dt minus M di2 by dt. So these two are also very important expressions. You will require them in solving problems. This is electromotive force. This is linkage, because this d by dt is actually electromotive force that I have done here. Okay. Minus, this is derived from this only. If you have any confusion, what I have done, this is E is what? It is d n1 phi 1 by dt minus, and n1 phi 1 is this. So I have written it like this. So you get electromotive force in one and this. So if you have electromotive force due to another coil, you'll have electromotive force due to the own property also, self-inductance also. So the total electromotive force will be this. Okay.